Thank you very much, and I thank the organizers for inviting me to give a talk here. So this talk is based on work which is joint with Mahan MJ and an ongoing joint work with Shomoshan Naik. The fiber product part is with Mahan and sorry, I don't have the and there is a relative property part which is going on with Shomoshan. So let me begin by telling you what is, reminding you what is the fiber product. So suppose you have two surjective group homomorphisms, and then you can take a fiber product, which is basically to take a point of the group H and look at the two fibers of the two homomorphisms and take their product and take union over all points of H. That gives you the fiber product. And in the particular case when the group H is trivial, you get the usual product. And in this case, it is known that if G1 and G2 have property T, then the product will also have property T. So it's a natural question to ask if in the fiber product case, the groups G1 and G2 have property T, then will the fiber product also have property T? And the answer is not always. But there is a very simple case in which the answer is always yes. So to say that, let me first note that the fiber product can always be put in a short exact sequence like this. And it is known for property T, general resultant property T says that if you have a short exact sequence in which the quotient group has property T, and the pair consisting of the middle group and the kernel here, if it has relative property T, then the middle group will also have property T. In fact, I should remind you what is relative property T. We saw yesterday that property T means that if a representation has almost invariant vector, then it must have a invariant vector. In case of relative property T, you have a pair of groups, group and a subgroup. So the relative property should say that if a representation of the bigger group has a almost invariant vectors, then there will be a invariant vector under the subgroup. So in this case, because G1, we know that G1 already has property T, it is enough to show that the middle group, the subgroup has relative property T. And the sufficient condition is that one of the maps splits. And if it splits, what we can do is, suppose the first homomorphism splits, then we can embed the second group inside the fiber product such that it contains the kernel 1 cross N2. And because G2 also has property T, this will imply that the pair will have relative property T, and that will do the job. Now let us look at some counterexamples. And in fact, in hindsight, the counterexamples, there are some, you can have a simple counterexample if you note the fact that if you take fiber product of two copies of the same homomorphism, it has the structure of a semidirect product, semidirect product of N and G, where N is the kernel of the homomorphism. And in this case, suppose N is contained in the center of G, then the G action on N is trivial, so the semidirect product becomes a product, and so N can be written as a quotient of G. And then if you take N to be non-compact, it is a non-compact abelian group, so it cannot have property T, so N semidirect product G cannot also have property T. And examples of property T groups having a center which is infinite is given by higher rank semisimple Lie groups, infinite covers of higher rank semisimple Lie groups, which is possible if you have Hermitian symmetric space of Hermitian type. And this is a result due to said that it can be the cover will also have property T. Another observation is that suppose you have that the groups G1 and G2 are finitely presented, but the group H is not finitely presented. In that case, the fiber product is not finitely generated. This is a result by Brightson and Miller, and therefore it cannot have property T. And there are many examples of non-finitely presented property T groups given by Margulis, Gromov, Cornulier. And we know that all of these groups must be quotients of some finitely generated group. And this is a celebrated result of Shalom. So here also you will find many examples. And we also had some more examples involving hyperbolically embedded subgroups, but it's not, I don't have time to explain that. Let us now concentrate on the case where we have two copies of the same homomorphism, and in this case, as I said before, it is a semidirect product, and then the question reduces to the question that if we know that the group G has property T, when can we say that the group's n semidirect product G also has property T? And the answer we are expecting should capture the feeling that, because G has property T, therefore it should be much easier to check whether n semidirect product G has property T. And in fact, we will characterize this in terms of representations of n and the J action. I mean, if you just want to look at property T of n semidirect product G, it is a statement about representations of n semidirect product G. But here we can only look at representations of n and the G action. To describe our results, we need to talk about the GNS correspondence. And the GNS correspondence basically tells you that instead of looking at representations, you can look at functional analysis on the group. So on the left-hand side, you have pairs of cyclic representations and cyclic vectors. And two such pairs will be equivalent if there is an intertwining operator which takes the cyclic vector to a cyclic vector, isometric intertwining operator. And on the right-hand side, you have a certain L infinity functions on G. I am not going to give a definition of it, but the way to go from one side to other is to just consider the diagonal matrix coefficient. And the interesting thing is that you can actually go back. That is the GNS construction. And I will denote, given a function of positive type phi, I will denote the representation corresponding it by putting the subscript phi. In the abelian case, in fact, you can look at measures, probability measures on the dual group, and functions of positive type and measures on probability measures on G hat correspond to each other via the Fourier transform. And in this case, in fact, you have a very explicit description of the representation, corresponding cyclic representation. You take a measure mu, it will give you a representation. The representation space is L2 of G hat with respect to the measure mu, and the cyclic vector is the constant function 1, and the action is basically pointwise product by evaluation map at G. So now let us look at the result that we have. We will assume that G and N are countable for this description, but we have our results are generally true for second countable locally compact groups. So suppose we know that G has property T, and then the equivalent condition for G, n semidirect product G to have property T, one of the equivalent conditions is that if you look at, you only have to look at functions of G invariant functions of positive type on n, and any such sequence, if it converges to the constant function 1, then it must converge uniformly to 1. So this result has that feature that your P1 G is basically just kind of representations of n, and we are looking at the G action only. So this is characterized in terms of these two things only. And then okay, we have I have not defined this NN. So this is functions conditionally of negative type, and they basically correspond to isometric action on Hilbert spaces. It's like a GNS correspondence in that context. And here the result is that if you take such G invariant functions, then they have to be bounded. And then I realized something which is which is like, I realized this after the paper was published, that you don't even need to look at all functions, G invariant functions of positive type. You just need to look at the extreme points of this convex set. And any sequence in this convex set that converges, you cannot have a sequence that converge pointwise to constant function in this. So it's like isolated. So it's similar to the result that property T is characterized by the fact that the trivial representation is isolated in the unitary dual. And then in the abelian case, we have a similar result which says that there is you only look at positively probability measures, G invariant probability measures on the dual group n hat, and you cannot have a sequence which converges to the Dirac mass at 1, so that none of the measures have an atom at 1. So if such a sequence exists, then it must have an atom at 1. So let me make one comment about this proof, which is that, as I said, in semidirect product G, when I am looking at property of that, we are looking at representations of the whole group n semidirect product G. But the equivalent conditions all deal with the representations of the subgroup N. And so at some point you have to, given a representation of N, you have to extend it to a representation of N semidirect product G. And this is the key step. So if you, let's start with a function of G invariant function of positive type, and then there is a GNS correspondence which gives me a cyclic representation with a cyclic vector. And how do I extend this representation to the whole group? We know that this is a G invariant function of positive type. Therefore, by uniqueness of GNS construction, you will have a unitary operator which intertwines the action of G dot pi phi and pi phi, and takes the cyclic vector to a cyclic vector. So if you take this isometry as the action of G, then this extends the representation to n semidirect product, and this is how you do it. Then let us move on to relative property. Now I am not assuming that G has property. I am just assuming that I'm asking the question that when does the semidirect product comma the normal part, when does it have property T? And there's a very nice result of Ioana, which says that in this case also, it is enough to look at representations of N and the G action on it. You don't need to look at the representation of N semidirect product G. And here the condition is in terms of sequences in sequences of probability measures on N hat, which are, last time we saw we took G invariant ones, but this time we will have a some kind of almost invariant measures. And again, if it converges to a Dirac path, then it must have some atom at one. So this result goes back to, like, one side of the result. The sufficient condition goes back to probably okay. Sorry. Okay. So this is the remark that, as I said, I like this result because relative property is being expressed only in terms of representation of N and the G action. And the if part goes back to Berger. And also I would like to say that this result has been generalized by Cornelier and Teixeira to second countable locally compact groups. And now let us, again, the key step here is extension of representation from N to N semidirect product G. And in this case, we cannot just extend it immediately. We have to do a modification. So if you are given a probability measure on N hat, then first you have to do an averaging over G like this, so that if you look at the push forward of the measure by G, then it is equivalent to the original measure in the sense of absolute continuity. So because you have absolute continuity, you will get a isometric intertwining operator from the corresponding measures, corresponding representation spaces, L2 n hat comma G star mu to L2 n hat mu by just multiplying the function with the square root of the Radon-Nikodym derivative. And this allows us to extend, you can define these operators pi mu G like this, and then you have to check that, and it is compatible, this from definition it will be compatible with the N action in the sense that pi mu of G and G inverse is equal to pi mu of G dot N. And one has to check that it is also a group homomorphism, that pi mu of G1, G2 is equal to pi mu of G1 into pi mu of G2. And that is, for that you have to check this cocycle condition on the Radon-Nikodym derivative, or rather the square root of the Radon-Nikodym derivative. In this case, the square root does not matter because we are just dealing with functions, so it's enough to check for the actual Radon-Nikodym derivatives. But I will go to a non-abelian setting now, in which case it won't be, this will cause a problem. So here is a proposed generalization of Iona's result. It says that, again, let's look at countable groups, and we would like to characterize relative property of a semidirect product. And again, we do it in terms of sequences of positively functions of positive type on n. And again, we have this almost invariance condition. So we look at almost invariant functions of positive type, and if it converges to the constant function 1 pointwise, then it must converge to it uniformly. And so at one level, this is just a translation of Iona's result. Using Fourier analysis, if you translate the result from measures to functions of positive type, this is what you get. But generally, such results are like not always true. I mean, the abelian case is very special. But in this case, I am fairly sure that this result is true, and we have more or less nailed down the proof. So let me again tell you about the main key step, which is again the extension of the a representation from n to n semidirect product G. In this case, we start with a function of positive type on n, and we again do this averaging over G, and what that will do is it will give us a kind of absolute continuity kind of thing. So G dot phi, it is a L infinity function. Phi and like all functions of positive type are L infinity functions, so we can think of them as duals of the L1 function. And what this says is that as linear functionals on L1n, they have to be positive. So now, analogous to the multiplication of square root by Ramanujan derivative in the abelian case, here also we'll have an isometric intertwining operator between the two GNS constructed spaces, representative spaces, V of G dot phi and V phi. And this is done by taking the unitary part of a polar decomposition of a natural unbounded intertwining operator that will come here. And this will allow us to extend the representation to the whole group, which is compatible with the action of n. But in this case, again, you have to check that these two, this is an actual group homomorphism. So this gets complicated because of the fact that I mentioned earlier that in the abelian case, we have to check a co-cycle condition in terms of the Radon-Nikodym derivatives, which are functions. And here, it is enough to check it for the squares of the function. And then immediately you will get the result for the square root also. But if you replace functions by operators, then there is a problem of commutation. Like Radon-Nikodym derivatives are functions, therefore they always commute. So you can always take the square root like this. But in general, you are taking square root of operators, and then you have to check that the two operators that we will be considering, they commute. And this requires an extra argument, and that probably I'm pretty sure that we have it now. And let me finish by asking for some applications. I mean, these are pretty theoretical results, but if you look at results of Burger or Shalom, they have used this a version of Iona's result to prove relative property for SL2Z, Z2. Even without going into SL2R, without taking the help of SL2R, SL2R semidirect product R2, R2. So in this case, because we were talking about property of automorphism groups of free groups yesterday, and we know that now we know that automorphism group of the free groups have property T, then we can ask whether the semidirect product with Fn also has property T, or in fact, whether the relative property T holds in this context. And I think it's not known. And also I don't know how to use our results to prove this, because functions of positive type on free groups are probably not that well understood. So yeah, that's my talk. Yeah, so the lower odd FNs do not have property T, we know that, but maybe the maybe the relative property still holds, like in case of, I don't know that. I'm just asking.
Thank you. Let's go for lunch and thank Andrei for